Welcome dear learners. We are continuing Unit 2 Chemical Bonding and Molecular Structure. In the present module, we are discussing hybridization. In this module, hybridization is there, salient features of hybridization, conditions for hybridization, orientation of hybrid orbitals, different type of hybridization and overview, and problems based on different aspects of hybridization. First of all, hybridization. Linus Pauling proposed that the valence atomic orbitals in the molecule are different from those in isolated atoms. This simply means that when atoms combine together to produce a molecule, the valence atomic orbitals of the molecule changes. Pauling introduced the concept of hybridization. Hybridization is defined as the process of intermixing of the orbitals of slightly different energies, resulting in the formation of new set of orbitals of equivalent energies and shape. That is, hybridization is the mixing up or combination of set of orbitals having nearly same energy. The result is a group of orbitals with identical energy and shape. We can exemplify the concept of hybridization by taking sp3 hybridization as an example. When one 2s and 3 2p orbitals of carbon hybridize, there occur the formation of 4 new sp3 hybrid orbitals. That is, in sp3 hybridization, 1s orbital and 3p orbital mixed up together to produce 4 identical sp3 hybrid orbitals. This is the pictorial representation of sp3 hybridization. Here you can see the participating orbitals, 1 2s orbital and 3p orbital, 3 2p orbitals, total of 4 orbitals mixed together. And this notation, one with a big lobe and another one with a next part with a small lobe, this represents the structure of a hybrid orbital. In sp3 hybridization, there are 4 such hybrid orbitals. That 4 such hybrid orbitals are arranged towards the 4 corners of a tetrahedron, and that arrangement is shown on the right end. So, this is the illustration or representation of sp3 hybridization. Once again, in sp3 hybridization, 1s orbital and 3p orbitals combine together to produce 4 sp3 hybrid orbitals which are arranged at the 4 corners of a tetrahedron. Now we are discussing salient features of hybridization. The hybridization is an important hypothetical concept. Now we are entering into the very important features or salient features of the concept of hybridization. First of all, the main features are the number of hybrid orbitals is equal to the number of atomic orbitals that get hybridized. This simply means that number of orbitals take part in hybridization is equal to number of hybrid orbitals produced. For example, in sp2 hybridization, 3 atomic orbitals, that is 1s orbital and 2p orbitals are involved, and as a result 3 sp2 hybrid orbitals are obtained. Look on the illustration part, 1s orbital, 2p orbitals can be seen there. They coupled together, they hybridized together, mixed together to produce the 3 sp2 hybrid orbitals which are arranged to the 3 corners of a triangle. So, in sp3 hybridization, 3 orbitals are participating and 3 sp2 hybrid orbitals are obtained. In every other case, you can apply the same condition. For instance, in the simplest hybridization, that is sp hybridization, 1s orbital and 1p orbital take part in hybridization, and as a result you are getting 2 sp hybrid orbitals. Moving on to the second salient feature, that is the hybrid orbitals are always equivalent in energy and shape. This is one of the most important aspect of the hybridization. The number of orbital take part may be different in energy as well as shape, but even though that is the situation, the hybrid orbitals obtained have identical energy as well as a shape. Consider sp3 hybridization as an example. 4 sp3 hybrid orbitals are obtained with equivalent energy and shape. So, in sp3 hybridization, one s px orbital, py orbital and pz orbital. That means 3 p orbitals combined with 1 s orbital to get to 4 sp3 hybrid orbital. All the sp3 hybrid orbital have identical energy as well as identical shape. Now, the third salient feature of hybridization is here. The hybrid orbitals are more effective in forming stable bonds than pure atomic orbitals. That is, the hybrid orbitals can have high efficacy in covalent bond formation compared to common atomic or unhybridized atomic orbitals. Now, the fourth salient feature of hybridization is that the hybrid orbitals are directed in space in some preferred directions to have minimum repulsion between electron pairs and the stable arrangement. That means the hybrid orbitals take orientations in such a way that there occur minimum repulsion between electrons present in them. So, the resultant geometry will be a more stable geometry. For example, in sp3 hybridization, the 4 sp3 hybrid orbitals show a tetrahedral arrangement. The tetrahedral arrangement is in such a way that there occur a bond angle of 109.5 degree or 109 degree 28 minute between the hybrid orbitals. The arrangement of 4 hybrid orbitals in a tetrahedral fashion is illustrated here. The fifth salient feature of hybridization is that the type of hybridization indicate the geometry of the molecule. That is, I already mentioned the fact that hybrid orbitals are arranged in space in such a way that there occur minimum repulsion between the electron pairs present in the hybrid orbitals. This leads to the suggestion that the type of hybridization indicate the geometry of the molecules obtained. This is a chart that is showing hybridization and geometry. In the first column, the hybridization is shown. In the second column, the corresponding geometry is also shown. For instance, the sp hybridization leads to linear geometry. sp2 hybridization gives trigonal planar geometry. sp3 hybridization gives tetrahedral geometry. sp3d hybridization produces trigonal bipyramidal geometry, and sp3d2 hybridization leads to the octahedral geometry. So, hybridization determines the geometry of the molecule. Now, we are discussing conditions for hybridization. We know about the definition of hybridization, that hybridization is the mixing up of atomic orbitals of nearly same energy to get a set of orbitals having identical energy and shape. Now, we are focusing on what are the necessary conditions for a hybridization. The important conditions are described here. The first condition is that the orbitals present in valence shell of the atom are undergo hybridization. The orbitals present in the inner shells will not participate in hybridization. This is because the valence electrons are take part, or valence shells are take part in chemical reaction, thereby indicating that orbitals of the valence shell only will undergo hybridization. The orbitals undergoing hybridization should have almost equal energy. This is an important requisite. The participating orbitals must have nearly same energy. Huge energy difference between the participating orbital prevent effective hybridization. Now, the third condition for hybridization is that promotion of electron from one orbital to another is not essential condition prior to hybridization. In certain cases, electronic excitation may occur. In some other cases, there is no need for the electronic excitation. That simply means that the promotion of electron from one orbital to another, or simply the promotion of electron, is not essential condition prior to hybridization. This is the fourth condition. It is not necessary that only half-filled orbitals participate in hybridization, and in some cases, even filled orbitals or filled orbitals of valence shell and vacant orbitals etc. can take part in hybridization. So, it is not necessary that only half-filled orbitals take part in hybridization. Now we are discussing orientation of hybrid orbitals. I just mentioned the fact that hybridization determines the geometry of the molecule. Why hybridization determines the geometry? Hybridization determines the geometry because hybrid orbitals have a definite orientation. The orientation of the hybrid orbital is in such a way that there occur minimum repulsion between electrons present in the hybrid orbital. So, hybrid orbitals have a definite orientation. This definite orientation leads it to definite geometry for a particular hybridization. So, hybridization can determine the geometry of the molecules. This is possible because hybrid orbitals have a definite orientation. Now we are discussing about the orientation of hybrid orbitals. The orientation of hybrid orbital is determined by the type of hybridization and the need to minimize electron repulsion, ensuring most stable molecular geometry. Let us go through the orientation of hybrid orbitals in different kind of hybridizations. First of all, we are taking sp hybridization. As the name indicates, there are two orbitals that take part in hybridization, and as a result, two sp hybrid orbitals are produced. The two sp hybrid orbitals are arranged in straight line with 180 degree separation, 180 degree apart, that is preferring a linear geometry. This is the arrangement of two sp hybrid orbitals. The two sp hybrid orbitals are oriented in a linear fashion such that the angle of separation between them is equal to 180 degree. This leads to linear geometry to molecules having sp hybridization. The second one is sp2 hybridization. As we know, in sp2 hybridization, three orbitals are take part in hybridization, 1s and 2p orbital. As a result, you are getting three sp2 hybrid orbitals. The three sp2 hybrid orbitals are arranged in a plane at 120 degree angles to each other. That means the geometry of sp2 hybrid orbital is trigonal planar geometry, which is shown here. You can see the presence of three sp2 hybrid orbitals. These three sp2 hybrid orbitals are separated by an angle of 120 degree, and this arrangement, this orientation leads it to trigonal planar geometry of molecules which possess sp2 hybridization. Moving on to sp3 hybridization, there are four sp3 hybrid orbitals produced during sp3 hybridization. The four sp3 hybrid orbitals adopt a tetrahedral orientation with a bond angle of 109.5 degree or in sharp 109 degree 28 minute. 30 minutes is equal to 0.5 degree. This is because 1 degree is equal to 60 minutes. This is the arrangement of four sp3 hybrid orbitals in a tetrahedral fashion. Here, the angle of separation between the two adjacent sp3 hybrid orbital is equal to 109.5 degree. The four sp3 hybrid orbitals on a sum produces a tetrahedral geometry, and this leads to the tetrahedral geometry of the molecules with the sp3 hybridization. Moving on to next hybridization, that is nothing but sp3d hybridization. The five hybrid orbitals are formed here, and these five hybrid orbitals are arranged themselves in a trigonal bipyramidal shape. Three equatorial orbitals at 120 degree and two axial orbitals at 90 degree as shown here. This about the trigonal bipyramidal arrangement of 5 sp3d hybrid orbitals, and the angle of separation between these sp3d hybrid orbitals are 2. In the in-plane bond angle is 120 degree and out of plane angle is 90 degree. So, the 5 sp3d hybrid orbitals, there are two type of bond angles, the 120 degree and 90 degree. This about the trigonal bipyramidal arrangement, which leads to trigonal bipyramidal geometry of molecules having sp3d hybridization. Moving on to next type of hybridization, that is nothing but sp3d2 hybridization. As we know, here there are 6 orbitals take part in hybridization and 6 sp3d2 hybrid orbitals are produced. These 6 sp3d hybrid orbitals are arranged in an octahedral shape, and the angle is 90 degree between them. This is the pictorial representation of the 6 sp3d2 hybrid orbitals, which are arranged in space in an octahedral fashion with an angle of separation 90 degree. And this arrangement, this orientation leads to octahedral geometry of the molecules which possess sp3d discussing different type of hybridization and overview. Or in coming few slides, we are discussing various kind of hybridization from a bird's eye. Hybridization is classified based on type and number of atomic orbitals involved. Each type results in a specific geometry and bond angles that determine the shape or geometry of the molecule. Let us have an overview on different common hybridization in simple molecules. First one, sp hybridization. Atomic orbitals involved in sp hybridization are one s orbital and one p orbital. Number of hybrid orbital, which is equal to number of orbitals that take part in hybridization, is 2. The geometry of sp hybridization is linear. The bond angle is 180 degree, and there are so many examples for molecules which possess sp hybridization. Some are here: beryllium chloride, carbon dioxide, C2H2 or ethane. In beryllium chloride, the central atom beryllium exhibits sp hybridization. In CO2, the central atom carbon shows sp hybridization, and in ethane, the central atom carbon exhibits sp hybridization. Now we are discussing the sp hybridization in beryllium chloride as a representative example. This about electronic arrangement of beryllium. The isolated beryllium atom is shown here, and in the case of beryllium, there occur the mixing up between one s orbital and one p orbital, and that leads to the generation of two sp hybrid orbital in beryllium. And these two sp hybrid orbitals of beryllium overlap with the half-filled p orbitals of chlorine, which leads to the formation of beryllium chloride, and the beryllium chloride molecule is linear molecule with 180 degree angle between them. So, in a sum, we can say that in beryllium there occur sp hybridization, which produces two sp hybrid orbitals which are at 180 degree away, and these two sp hybrid orbital overlap with the half-filled 2pz orbitals of chlorine to produce beryllium chloride molecule, and the beryllium chloride molecule is linear with a bond angle of 180 degree. Moving on to second hybridization, this is another popular hybridization of simple molecule, that is nothing but sp2 hybridization. Atomic orbitals involved are here 1s orbital and 2p orbital, so a total of 3 orbitals that take part in hybridization, and as a result, number of hybrid orbital produced will be equal to 3, and the geometry, the preferred geometry will be trigonal planar geometry, and the bond angle here is 120 degree. Examples include boron trifluoride or any boron halides can be taken as the example. BF3, BCl3, BBr3, BA3 all have sp2 hybridization with respect to central atom boron, and the next molecule is C2H4, that is ethene. Here the central atom carbon exhibit sp2 hybridization, and the final example is sulfur trioxide, where also the central atom sulfur shows sp2 hybridization. Now we can illustrate sp2 hybridization by taking BF3 molecule as an example. That is, we are discussing the sp2 hybridization in BF3. So, this is the electronic arrangement of boron. Boron is having an electronic arrangement 2s to 2p1. Both electronic arrangement in 2s orbital and 2p orbital are shown here. They will mix together to produce 3 sp2 hybrid orbitals, and these 3 sp2 hybrid orbitals present on the boron atom overlap with the 3 half-filled p orbitals of the fluorine to form BF3 molecule with an angle of separation equal to 120 degree, or the bond angle is 120 degree, and the resultant geometry or molecule is called trigonal planar shape or trigonal planar geometry. Now we are discussing sp3 hybridization. As the name indicates, one s orbital and 3 p orbital take part in hybridization here. So, the number of atomic orbitals involved is equal to 1 s orbital and 3 p orbitals. This ultimately leads to the production of 4 hybrid orbitals known as 4 sp3 hybrid orbitals. These 4 sp3 hybrid orbitals prefer a tetrahedral geometry and it offers tetrahedral geometry to the molecule also. And the bond angle in tetrahedral arrangement is 109 degree 28 minute. So the molecules with the pure sp3 hybridization exhibit a bond angle of 109 degree 28 minute. And there are so many examples. The most popular example is methane. Here there is no lone pair on the central atom. So methane molecule is having geometry as well as shape similar to both are same, both are tetrahedron. But in the case of ammonia molecule, you know there is a lone pair of on nitrogen atom, and excluding that nitrogen atom, excluding that lone pair, the ammonia molecule exhibit a pyramidal shape. In water molecule, there occur the presence of two lone pairs on the central atom oxygen, and that leads it to bend shape. However, the geometry remains the same. This is because for a particular hybridization, the geometry is a constant. All these molecules, even though have a different shape, all possess tetrahedral geometry, and that tetrahedral geometry is due to sp3 hybridization. We can enter into more details of the difference between geometry and shape in coming modules. Now we are illustrating sp3 hybridization in CH4. This is the electronic arrangement of the central atom carbon in CH4. Carbon is having an electronic configuration 2s2 2p2, which is shown here. These orbitals, one s orbital and 3 p orbitals, undergo mixing up to produce the sp3 hybridization. Prior to sp3 hybridization, one electron from 2s orbital is simply jumped to the 2p orbital. So you are getting 4 half-filled atomic orbital. These 4 half-filled atomic orbitals is having different energy. Now they undergo hybridization to produce 4 sp3 hybrid orbitals with the identical energy and shape. The 4 sp3 hybrid orbitals on carbon may overlap with the s orbital of hydrogen to produce the CH4 molecule with the tetrahedral shape. That is, CH4 molecule shows tetrahedral shape. This is due to the hybridization sp3 for the central atom carbon. Now we are looking on to sp3 hybridization in ammonia molecule. I already mentioned the fact that in ammonia molecule, the central atom nitrogen has a lone pair of electron, and the electronic arrangement is here. 2s2 2p3 is the electronic arrangement. During mixing up, there occur 2 electrons, an electron pair on one sp3 hybrid orbital, and 3 other sp3 hybrid orbitals are half-filled. So among 4 sp3 hybrid orbitals in nitrogen, one is completely filled, that is due to the presence of the lone pair. 3 other sp3 hybrid orbitals are half-filled, and these 3 sp3 hybrid orbital overlap with the 1s orbital of hydrogen to produce the ammonia molecule. So in ammonia molecule, in the nitrogen atom, there is a lone pair and 3 bond pair. So the ammonia molecule prefers to have a tetrahedral geometry with 1 position occupied by lone pair and 3 other position occupied by NH bonds. Excluding the contribution from the lone pair, you can arrive at the shape of ammonia molecule. That is, the shape of ammonia molecule is pyramidal and the geometry is tetrahedral with 1 position occupied by lone pair. Now we are entering into another popular hybridization, that is nothing but sp3d hybridization. As the name indicates, in sp3d hybridization, 1 s orbital, 3 p orbital and 1 d orbital take part in hybridization. So the number of atomic orbitals involved, as I mentioned, 1 s orbital, 3 p orbital and 1 d orbital. During the mixing up of 5 orbitals, there occur the generation of 5 hybrid orbitals. So number of hybrid orbitals is equal to 5. That is, 5 sp3d hybrid orbitals are produced during sp3d hybridization. The geometry of sp3d hybridization is nothing but trigonal bipyramidal geometry, and there are 2 bond angles. The bond angles are 90 degree and 120 degree. In plane bond angle is 120 degree and the next bond angle is 90 degree. Typical examples of molecules with the sp3d hybridization involves PCl5, that is phosphorus pentachloride, SF4 sulfur tetrafluoride and ClF3 chlorine trifluoride. Now we can illustrate sp3d hybridization in phosphorus pentachloride, or we are taking PCl5 as an example to illustrate the sp3d hybridization. This is the electronic arrangement of isolated phosphorus atom, which is having an electronic configuration of 3s2 3p3 3d0, out of which 1 s orbital 3 p orbital and 1 d orbital undergo mixing up to produce 5 sp3d hybrid orbitals. These 5 sp3d hybrid orbitals are half-filled due to electronic excitation, and these half-filled 5 sp3d hybrid orbitals overlap with the 2pz orbital of chlorine atom to form the PCl5 molecule, and this is the structure of the PCl5 molecule. The PCl5 molecule, you can see two bond angles, the in-plane bond angle of 120 degree and the next bond angle of 90 degree. So the molecule has trigonal bipyramidal shape. Since there is no lone pair of electron on the central atom phosphorus, the molecule exhibit trigonal bipyramidal shape as well as trigonal bipyramidal geometry. Now we are discussing sp3d2 hybridization. From this notation, it is very well clear that there are 6 orbitals that take part in hybridization. So the atomic orbitals involved in sp3d2 hybridization are 1 s orbital, 3 p orbitals and 2 d orbitals. As a result, 6 sp3d2 hybrid orbitals are obtained. So number of hybrid orbitals produced is equal to 6, and the molecule prefers to have, or sp3d2 hybridization implies an octahedral geometry. The octahedron has a bond angle of 90 degree. So the bond angle in sp3d2 hybridization is 90 degree. There are many examples for molecules showing sp3d2 hybridization. The popular examples involve SF6, that is sulfur hexafluoride, HCl4, that is nothing but xenon tetrafluoride. Now we can illustrate the sp3d2 hybridization by taking SF6 molecule as an example. In SF6 molecule, the central atom sulfur exhibit sp3d2 hybridization, and that is notated here, that is shown here. The central atom sulfur has an electronic configuration in its isolated state as 3s2, 3p4, 3d0, and during the mixing up of 1s orbital, 3p orbital and 2d orbital, we will get 6 sp3d2 hybrid orbitals. All these hybrid orbitals of SF6, the central atom sulfur, has half-filled arrangement. These 6 half-filled sp3d2 hybrid orbitals overlap with half-filled pz orbitals of 6 fluorine atoms to produce the SF6 molecule. The SF6 molecule has an octahedral arrangement as shown here. The bond angle is equal to 90 degree. Thus we can say that the molecule, the SF6 molecule, has octahedral shape. Now we can consolidate various type of hybridization in a chart form like this. The first column represents hybridization. Second column represents orbitals mixed. Number of hybrid orbitals are produced in the third column. Geometry is shown in fourth column, and bond angles are shown in the last column. Let us go through all the popular hybridizations. The 5 hybridizations are shown here. sp hybridization leads it to the geometry linear with a bond angle of 180 degree. sp2 hybridization leads to trigonal planar geometry with a bond angle of 120 degree. sp3 hybridization leads to tetrahedral geometry with a bond angle of 109.5 degree. sp3d hybridization leads to trigonal bipyramidal geometry with the 2 bond angles, that is nothing but 90 degree and 120 degree. And finally, sp3d2 hybridization involves the generation of 6 hybrid orbitals with the octahedral geometry, and the bond angle is 90 degree. That all about the consolidation of hybridization. Now we can have some problems based on the concept of hybridization that we have learned so far. The first MCQ in front of you is this: which of the following molecules shows sp hybridization? These are the 4 options: CH4, carbon dioxide, ammonia and BF3. On careful analysis of the 4 options, you can arrive at the conclusion that your answer is option B, carbon dioxide. In carbon dioxide molecule, the central atom carbon exhibit sp hybridization. It is associated with a linear shape. This is the second MCQ. Which of the following statements is correct regarding hybridization? These are the statements in front of you. The number of hybrid orbitals is always greater than number of atomic orbitals. The second option, the number of hybrid orbital is equal to number of atomic orbitals mixed. The third option, the number of hybrid orbitals is always less than the number of atomic orbitals. And finally, the last option, hybrid orbitals are not related to molecular geometry. On careful checking of these four options, you can arrive at the final answer as option B, that is the number of hybrid orbitals is equal to number of atomic orbitals mixed. That is the very basic principle of hybridization. Moving on to next MCQ, which of the following molecules has an octahedral shape? The question is about the shape. These are the options: SF4, PCl5, CH4 and ammonia. It is very well clear that your answer is option A, that is sulfur hexafluoride. SF6 is a molecule where the central atom sulfur exhibit the sp3d2 hybridization, so it is associated with the regular octahedral shape or octahedral geometry. Now another MCQ, a molecule has a central atom with sp2 hybridization and one lone pair. What could be its possible shape? It should be noted that whenever you are mentioning the shape, you have to exclude the lone pair. And these are the options. Option A, trigonal planar. Option B, bent. Option C, tetrahedral. Option D, seesaw arrangement. And it should be noted that the hybridization is sp2 and there is one lone pair also. So, the arrangement, the shape of the molecule will be option 2, that is bend. So, the molecule prefers to have a bend shape. If there is no lone pair, the molecule will be trigonal planar. So, in trigonal planar arrangement, geometry will be trigonal planar for sp2 hybridization, but there occur a lone pair. So, one corner of the triangle is occupied by lone pair. You have to exclude that lone pair to specify the shape. On excluding that lone pair, you will get a bend shape. So, the sp2 hybridization with one lone pair leads it to a bend shape. Now, we are discussing another MCQ. In HCF4 molecule, what is the geometry and hybridization? These are the options: square planar geometry, sp3d2 hybridization, trigonal bipyramidal with sp3d hybridization, octahedral sp3d2 and tetrahedral sp3. On careful analysis of the four options, you can arrive at the final answer as option A, square planar with sp3d2 hybridization. sp3d2 hybridization implies octahedral geometry, but in HCF4 there are two lone pairs. Excluding that lone pair, you will get a square planar shape. So, in HCF4 molecule, the shape will be square planar, but the hybridization will be sp3d2. This is the last MCQ. In which of the following molecules does the central atom undergo sp3d hybridization, but the molecular shape is not a trigonal bipyramidal? This question clearly implies that there occur the presence of some lone pairs. That's why geometry different from trigonal bipyramidal, shape different from trigonal bipyramidal. These are the options in front of you. Option A, PCl5, option B, SF4, option C, PF2, Cl3, option D, SbF5. On careful analysis, you can arrive at the final answer as option B, that is SF4. In SF4, the central atom sulfur exhibit sp3d hybridization and we are anticipating a trigonal bipyramidal shape, but there is a lone pair. You have to exclude that lone pair. On excluding that lone pair from the trigonal bipyramidal geometry, you will get a different shape. That shape is called a seesaw shape. We can enter into more details of shape and geometry in coming modules. That all about the present module. Have a nice learning experience. Thank you.